138. Multiple choice. If f is differentiable, able to be derived, the derivative exists at x equals c, which of the following could be false? Letter A, must be true, could be false. Must be true, because according to our forever card, a function is only differentiable if first it is continuous. Well, that's not the answer. Letter B, the limit as x approaches c exists. Wait, doesn't that sound like a part of the forever card, the definition of continuous? Well, if it's continuous, doesn't that mean that has to be true? Right? Okay, letter C, f prime of c is defined. If it's differentiable, it's able to be derived, which means the derivative must exist. Does that make sense? The only one that we're not guaranteed is the, who is that? How do we say that? Do you remember?
That's right.
We talked about just a little bit, f double prime, or we could say the second derivative of function f. It's two little apostrophes instead of one.
You're right, that looks like the same as the end. Yeah.
And last night, did any of you guys practice the second derivative questions? Did you persevere through and figure it out? You take a first derivative, and how do you find a second derivative?
Take it again.
You go again. Are they two different things? Yes. One is the first derivative. Oh my goodness, you guys are hilarious.
What does that mean?
Then you do it again. Okay, so,
I don't know.
number 139.
Scrubbed really angrily.
What is the only proper way to start? Derive using the
I did something really
The
stupid.
only proper way would be the product rule.
Something really stupid.
Some of you might have made cotangent, cosine over sine. You're making your life so much more difficult. There's a rule for this now. So dy dx would equal. How does the product rule work? You help me.
The second one, you write it down.
Second d first, so write down the second. Oh, it's not cosine, lo siento, it's cotangent, right? What's the derivative of the first? I'm writing the second. Second,
Corey?
d first. Keep the 4. Keep the e to the x, right? Second d first. Plus first, rewrite it. D second. Yesterday we saw that we can't actually figure the derivative of cotangent out from the quotient rule of cosine over sine, but what ended up happening? What did it end up equaling at the end of the day?
Negative cosecant.
Negative cosecant squared. Hey, let's just pause and not waste time rewriting and see if we can make it match. For instance, letter A, yeah, no, e to the x minus 1 doesn't even make sense. Letter B doesn't have a minus. Letter C, well, that's looking better. Okay, hold on, which one's which? What did they do with the 4 e to the x? Pulled it out of there, and what was left? Cotangent minus cosecant squared. If you're in a multiple choice question, try to make it match as quickly as possible. Just don't make mistakes while you're doing it. Okay, number 140. What is the second derivative? All right, we talked about this just a second ago. How do we find, just a second ago, that's funny. How do we find a second derivative?
Derivative is the first derivative.
You go once, and then you go again. So h prime, what's the only legal way of progressing with this problem? Seeing it as a quotient. So bottom d top, did you guys do it? Minus top d bottom all over bottom squared. You guys double check. Do you think we want to take a derivative right now with the top and bottom, or do we want to simplify, make it pretty, and then? Oh yeah, so it's really worth being self-serving right now. Trying to make it easier before we take another derivative. So that up top we end up with, long story short, there should be a 2x squared minus a 1x squared, which will be a single x squared. I'm going quick. A minus 1x plus a 10x, which would be a 9x plus an x, which would be a 10x. Then we have minus 5 and no other constants. Does that look about right?
Yep.
Was that able to factor down?
No.
No, 5 and 1 can't make 10. Alright, well we're stuck. That's the, what do we call this? H prime, the derivative, but technically which one?
First.
The first derivative. So how do we go? Again? Here we go. Quotient rule. One more. Oh, stink. You don't know how to do this quotient rule technically. What's the answer?
There's another
What?
1 second.
We still did it.
We haven't, you can still do it, except some of you will have done it incorrectly. We don't know how to take a derivative of something squared like that. We could do x plus 5 times x plus 5 product rule in a quotient rule. No, thank you. Why don't we just go ahead and make him who he is? Okay, now we can do the quotient rule. Now we can do the quotient.
Helen.
Alright, h double prime of x. We need section 2.4 for that, and obviously we haven't done that one yet. Bottom to top. Ew. X squared plus 10x plus 25. Derivative of the top is 2x plus 10. Ooh. Minus.
Oh yeah, it doesn't even end.
Top to bottom. Bottom to top minus top. To bottom.
If you square that, then you get x.
All over bottom squared, which this was x plus 5 squared, so we can't make it x plus 5 to the 4th. That's legal.
There we go. We're done.
We're done. Stick it to the man. Which one? I don't think it's A. Okay, but we technically would have to simplify. Lo siento, it is true. We can make that x plus 5 squared. That doesn't really help us much. How would we technically simplify? Wait. Quick AP trick. Weird, but true, and hopefully grouping helps you see this. How many pieces are there up top? 2. And what do they both have?
2x minus 2x plus 10.
So instead of distributing and making this look awful, since there is a shared factor, what could we do with it? We can pull it out, just like we did with grouping a long time ago. And what would be left? Let's see if this makes it easier. Well, with that gone, all we have is x squared plus 10x plus 25 minus, don't kill his seal, there's a parenthesis, x squared plus 10x minus 5?
Well, you distributed it.
I haven't distributed it yet. It's minus 5, right?
Yeah.
Okay.
Yeah, it's minus.
All over x plus 5 to the 4th. Oh my goodness. What can come out of this?
Simplify.
Oh my
Oh, wow.
goodness. One can go away.
No, 60. Oh.
Right? Right? He's out here. That stuff I can't cancel anything. That's killing a poor little kitten. But it's factored out and I have an x plus 5. Now there's still a 2 remaining. I'm going to distribute my little negative. Alan, this would have been one that might have taken a little bit more than 1.2. X squared, gone. 10x is gone. 25 plus 5 is 30. 30 times 2 is 60. Still there. Oh my.
So you see something nice and even like 60 and you're like, that can't be the answer, it's not that simple.
Well, it wasn't that simple, right? But the answer did simplify. Simple and simplify is different. Okay, number 141. I know. It was amazing. Number 141. What? Feet? Huh? Let f of x equal, here's our function. And f represent the whose derivative? The nth derivative. Which could be, if n was 1, the first derivative, n was 2, the second derivative, if n was 3, the third, if n was 4, the fourth and fifth and sixth. That's why they put the th, because that's what most it's will be. They're asking, when will the derivative equal the function? How can they ask that? What's the first nothing else, you just start going. What's the first derivative of my function?
Cosine plus sine.
Cosine plus minus a negative sine. That's not the same.
Always get it wrong.
Oh, it needs to be the same. Take the second derivative. Negative sine of x plus cosine of x. Negative is, by the wrong one, right? That's not the same. Take the third derivative, which means go again. Are we all paying attention and we're in our notes and working on the examples and not on anything else? Just tracking. What's the derivative of negative sine?
Cosine.
And what's the derivative of cosine?
Negative sine.
Oh my word, still not the same. Take a fourth derivative. Now, we could put a little 4 in parentheses. We could also put a little Roman numeral 4. Both of them mean fourth derivative. We can keep on going with the 5th and the 6th and the 7th in the sense of Roman numerals. These are technically little apostrophes, and then we kind of go to Roman numerals to make it easy. Or we could put little f parenthesis 4. Derivative of negative cosine. Negative sign, which is a positive sign, minus a cosine. Oh my goodness. It matches. Which derivative?
Go back in time and punch Thomas. No.
4.
Isaac Newton.
Derivatives and sines and cosines, added and subtracted, and always cycle back. All right, it was crazy, it was intense, it might have been a little bit rough. However, do we at least have the right answers now?
Say Thomas Jefferson.
Okay, and it's recorded if you want to go back and re-listen to any explanations. Kiddos, yesterday, in section 2-3, which that homework, yes, I wanted you to fully attempt, we ended kind of here. But did any of you guys get this? Nope. Did any of you guys get this in your notes? No. Alright, let's pause for a second. Keep your spirals close just in case we do have time to go peek at 2-3 homework. I would love to be able to check the beginning of 2-3, kind of end when it started getting to the stuff that we didn't get to practice yesterday. We are definitely going to figure out a way to get into 2-4 today, but I did kind of adjust the calendar this morning and everything is bumped today. Everything is bumped today, which means that homework 2-4 is not due until Monday. You could kind of think about 2-3 totally finished due tomorrow. Hopefully you really, really attempted it tonight so you don't have to do tons more work on it. But some of you, I know, you needed a bit more work on it. So let's go ahead and get some stuff down. Let's do 2 quick examples, and then we're moving on. Sound good? Yeah. And 1 forever card. And 1 forever card. None of this is you guys, right? No, it's pre-cal. Ooh, whose forever cards though? Oh, no. Looks very worn though. I think it's a baby kid.
That's yours. Those are yours.
Mine. Mine?
Yeah, I stole them out of the cabinet the other day.
Oh, some kid left them last year. Who left them?
Can I take them?
Is it nice
No.
inside?
No, it's really
Because
good.
writing helps you memorize. And I kind of changed them. Like for instance, with our new book, things are in different orders this year. So I don't want to mess you up that way.
Do you have a whole other set of forever cards for these?
First of all, whole nother isn't a phrase.
Not whole as in 49 cards, though. We usually do about 40, 35.
We do 49 cards, we don't do 50.
Is that all of you?
I think we might do 50 this year.
Let's make it
Last
51.
year we went up to 49, but we also had a forever A for like pre-cal stuff, which was all the trig stuff. This year I was like, forget it, we're starting at 1 and just going. We might go to 50.
Let's go to 51.
Ooh.
Just the bottom.
Just get one of those with
What do you guys see?
Sort of bottom.
A lot of letters. This notation, y prime, y double prime, triple prime, 4th prime, 5th prime? Sorry, dot, 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 nth prime. Technically there's a dot, dot, dot. They did it over here. We could keep on doing it in all of the columns. We've kind of seen all of these notations. It just gets a little funny when we start going to 2nd and 3rd and 4th derivatives. Hopefully the primes kind of make sense. Y prime prime, so take another derivative. Y prime, y double prime primed again. Take a triple. It's a triple derivative. Same thing with the function notation, f prime, f double prime, f triple prime after the 4th. And I also showed you that there could be little Roman numerals there instead of the little normal numbers in the parentheses. This notation gets a little funny. This notation gets a little funny. Because the first derivative, we've memorized that. Second derivative, ooh, the d is squared with the y and then the dx is squared. But if you think about it, you're taking d dx twice. So the d in essence, I mean, it's not perfectly matching up, but the notation does fit with what hopefully we would think. D dx and d dx again, the d would be squared and then the dx would be squared of who? Of y. That's where that notation comes in. So remember, these are nouns, and these are showing the actual action of take the derivative twice, take the derivative 3 times, 4 times, etc. And this is that snazzy, I don't know, like programming language that we rarely see. But technically it would also work with the first derivative, take the derivative twice, 3 times, 4 times, with respect to x of y. But anyway, those are all the different ways of noting all the different derivatives. What we saw yesterday was as long as there is my goodness, as long as there is differentiability. Oh, some of you guys didn't get pictures. Pass back to Josh. Brandon. As long as there is differentiability. Oh, what does that mean? As long as you can keep taking the derivative and it exists. That's what that means. As long as there is differentiability. And non-trivial, we'll see it in a second, derivatives. We can keep taking higher order derivatives. Now, just because you can do something doesn't mean you necessarily should do something, right? Life lesson. But, coming back. In calculus, just because you can keep going, you have to look at the question being given. And if they say find f prime, if they say find dy dx, if they say find the derivative, and that's all they say, who are they talking about? The first, which is why we've been working with him quite a while before talking about the rest. But there are some places, maybe they'll tell you find the second or the third or the fourth, or keep taking more and more derivatives until they become trivial, or some other type of direction. Maybe they'll say something like that, which means keep going, but otherwise you should find the first, deal with the first. Maybe they'll give you clues in the problem that point to a certain derivative. Like maybe they'll say find velocity and not say average, which means take the first derivative of position. Maybe they'll say find acceleration, which as we'll write down in a second, and we barely saw yesterday, means take the second derivative of position or the first derivative of velocity. So they might put some words in there that mean one of these derivatives. But once again, if they are just asking for y prime or f prime or dy dx or the derivative, they always mean the first, okay? Now, with that, are we close? What if I put in the directions, find all, all? You just saw it was infinitely many. Kind of, there's some conditions though. Find all the higher derivatives of the given function. Where would you start?
The first one.
First one, f prime equals, come on amazing ones, power rule, easy cheesy, right? 15x squared
Plus 14x.
plus 14x minus 4. No. Common mistake. Derivative of negative 4 is 0. Okay, he's gone, right? Can we keep going? Sure, why not? Second derivative. Practice your little notation. F double prime. Which will be, bring down the 2, 30x plus, bring down the 1, powers disappear, we just have 14. Can we go again? Sure, why not? F triple prime, or the third derivative of x. 30. Do you see how this poor little guy is like breaking down as we derive?
Yeah.
Powers will always. Powers will always. Fourth derivative. We can take it. The fifth derivative.
0.
Do you see how now they're trivial? They're trivial. They're all going to be 0. They're all going to be 0. There is, since this fourth derivative is 0, nothing past this point, nothing is changing anymore. If you think of this in terms of motion, one possible example, this could be position. This is the rate of change of position. So this would be feet per second, feet per second per second. This is how fast he's changing, 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 and he's not, so then nothing else will be changing. Another way of looking at it. Okay? So do you get now what trivial means? Oh, they're all 0. Does every function get to a place where everything is 0? No, but powers will always. It might just take a while. How long did it take for this one to break down to 0? 4 derivatives. Oh, there were 3 x to the 3rd power. The degree was 3. Huh. How long do you think it would take a second degree to break down? 3. A first degree? 2. Because you can always take the derivative of the constant at the end, so there's always 1. So how long would it take for a 20th power to break down? 21. Okay. We briefly talked about acceleration yesterday. So an application of a higher order derivative. Acceleration is the rate of change of velocity. It describes how velocity is changing. If you look at your speedometer, you take a picture. Whatever number it's on denotes per 1 hour how many miles you would go, right? Miles per hour. But if you were able to numerically describe your acceleration at some point, it would say, if it's in the same units, so hours is time, miles is distance, it would be per hour how quickly your miles per hour is changing. So it'd be miles per hour is another per hour, or miles per hour squared. Acceleration, you put your foot on the pedal, and isn't your distance still changing? Yes, but what else is now changing? Your speed or your velocity with direction. If your acceleration was 0, could you be moving?
Constant.
Yes.
Well,
yes, because what if
What
your
would be
speed was
going on
constant?
if your acceleration, you're right. What would be going on if your acceleration was 0?
Your speed can be constant.
You're not accelerating or decelerating. You're cruising, right? Now, could your acceleration be 0 and your velocity be 0, like you're stopped and nothing's going on, you're not hitting the pedal? Yeah, that's one example, but couldn't you also be going 60 and be on cruise control? Let's pretend it's actually holding it, right? Your acceleration is 0 because you're just going, unless there's a hill, then of course your engine is working, but that's a different scenario. Okay, so acceleration, the rate of change of velocity. How do we do rate of change? If it doesn't say average, we're taking a, hold on, how do we do rate of change? If it doesn't say average, derivative.
Instantaneous.
Yeah, it's instantaneous if it doesn't say average. We're taking a derivative. So we could change this to say d dt of velocity. We can say d dt of velocity. And substituting, we can say, hold on, who is velocity again? Velocity is the rate of change of position. So velocity was, position is s, commonly in our book anyway, s prime, right? And if we take a derivative of a derivative, what are we actually taking? A second derivative. So I could call acceleration v prime, first derivative of velocity, or s double prime, the second derivative of position. And to incorporate a new letter, this would be acceleration. So all of that, let's just peek at this example. The velocity of an automobile starting from rest is v of t equals, nasty equation, 100t over 2t plus 15. V is measured in feet per second. Find the acceleration at, how do we do acceleration? Look at what you have and ask yourself, is it a single prime or a double prime? Single prime. They already gave me velocity. If they gave me position, it would be a double prime. So I need to go ahead and take velocity, and all I need is one derivative. But if they gave me position, I would need a double derivative or a second derivative. I would need to go twice. So acceleration is going to equal bottom. What am I using? Got it. D top, that's 100t. Sorry, I covered it up a little. numerator. There we go. Minus, you guys are doing the minus, not the plus, right? Minus top d bottom all over bottom squared. Bottom d top minus top d bottom all over bottom squared. Simplifying just to make it easier on me later on. I guess I could pull 100 out of everything. Do you guys see? We're practicing. Do you guys see how 100 is in both?
Yeah.
So let's pull the 100 out of both. There are two parts up top. I end up with 2t plus 15 minus, the 100 is gone, 2t. Oh hey, 2t minus 2t, isn't that just gone? Some of you, in homework, you've already made the common mistake of forgetting the denominator. Keep rewriting him, don't lose him. And so we end up with 15 times 100, 1500, yeah? All over 2t plus 15. Cool. Who is he? Acceleration. What are they actually asking for?
At a certain point.
At certain points. So I just need to go ahead and find a of 5. A of 10. A, that's a horrible A, of 20. To find it, all we gotta do is plug it in, right?
Yeah.
Plugging in 5 to do it fast. 2 times 5 is 10, 10 plus 15 is 25, 25 squared is,
625, right?
genius. Because 25 times 5 is 125, 125 times, yeah, 625. And I'm sure we could reduce. Does anybody have a calculator close?
2.4.
2.4. And what would the units be? Let me help you out. If velocity is feet per second, acceleration says how many feet per second per second. So it's feet per second squared. If I was to plug in 10, I would have 1500, let's stop doing this mentally, times 2 times 10 is 20, 20 plus, that'd be 35. Just kidding, I'm kind of still doing it. What'd you guys get when you plug in?
60 over 49 or 1.22.
1.22 feet per second squared. And last but not least, 1500. All over 2 times 20 is 40 plus 15 is 55 squared, which would end up being
0.496.
feet per second squared. Oh. Don't know what I'm doing. Done. Okay. So, nice thing is, this is number 122, and guess which one you have in your homework? Number 121. So, we're done with section 2.3. So let's go ahead and just take one page, because some of you guys have been needing this, and I wanted to get through acceleration before we did it. And let's summarize what we know about motion, okay? Let's summarize what we know about motion. First of all, position. Position is frequently measured in, well, we'll do that over here. Position is normally denoted S of t, and I'm going to help you out because sometimes it could be called, for our rectilinear motion, x of t. Our book uses S a lot, so that's all we've had to worry about. And position is measured in, could be feet,
Just distance.
could be miles, could be meters, could be some unit that denotes length or distance. Does that make sense? Velocity. He's just v of t. In general. What is he measured in? Depends. But depending on what we have, he could be in miles per hour, a distance over a time. He could be something like feet per second. He could be something like meters per minute. I'm just making up stuff now, but long story short, he could be anything that has some sort of distance measurement over some sort of time measurement. And why is that true? Because average velocity is change in position over change in time, and they always give some sort of interval for which we're supposed to find average. They have to give us 2 different times. And you guys should have seen that in your homework for 2-2b. Instantaneous, or if they just don't say average, remember we were talking about that? They're talking about finding the velocity function by taking s prime, which technically stands for ds dt, which is where, once again, we get the velocity measurements of positions over times. Well, you can see it here, positions over times. Speed, what is his relationship? He's velocity, but just velocity's magnitude, hence absolute value of velocity. He's always positive. Velocity has direction. Speed, absolute value of velocity. So his measurements are going to be, in essence, the same, just his signs are going to be always positive. And then the last one that we just talked about, acceleration. Can be denoted a couple different ways, but he's either the first derivative if you're given velocity, or he's the second derivative if you're given position, and his measurements would be just like velocity but with an extra per hour. Just like feet per second, but with an extra per second. Just like meters per minute, but with an extra per minute. Squared's only on the bottom, not on the top. This is a forever number. I think we need to have a quiz soon, huh? But the nice thing is, pause, first of all, I think it's forever number 12. 12, yes. Because 11 were the trig derivatives, and 10 was the product quotient rule, all together one card. But hold on, shouldn't you guys have the product quotient rule memorized by the time we get to a quiz?
Yeah.
How about the constant rule, or the power rule, or the multiple rule, or a lot of these things hopefully you're just going to have memorized just by doing the problems, but there's always a place for study. Because of how time has gone, instead of checking product rule, quotient rule, let's just save all of that for first thing tomorrow. We won't have a warm-up or anything like that. Have your colored pens out and ready to go. After we watch HTTV, we will check 2, 3. It was a mammoth meeting. If you think about it, you've been given about 3 nights for it. That's a long time. And I've tried to do lots of examples to help. Sound good? Okay. We are going to, instead of checking 2, 3, let's just say this could kind of get messy sometimes. But nice thing is, this is number 18 from the old book. So hopefully none of yours will be quite that bad. You just gotta keep going one step at a time. Yeah, it took a little while. All right. What? Section 2.4.
Remind me of the Matryoshka doll.
Section 2.4.
That was good.
Section 2.4. We'll come back to the Matryoshkas in just a second. Already? Still have 2 more minutes. Good try. E for effort. I'd miss you guys too much. Maybe 1 more minute. Okay, 2.4. The chain rule. Has anybody ever seen these up here since last year and wondered what they were here for?
Yes.
Aw, where are they? Oh, so they got stuck. The little one's missing. Oh, this is too sad. Andrew Aguinaldo told me to make it pretty, but I'm missing my baby one. Anyway, they're Matryoshkas. There's an outer, there's a middle, there's an inner. What did we talk about in pre-cal that had outers and inners?
Not foil.
Not foil. Outers and inners. Okay, foil. Foil had an outer multiplication, inner multiplication. But what had an outer part or shell and an inner, all right, fine, component? Does that help? Huh?
Pascal's
What'd you say, Angela? I didn't hear you. Almost. It wasn't called component. Composite functions. Composite functions. Composite functions have outer and inners. And there was this pre-cal thing that we did last year. as you guys are writing up on the board, where we would take some funny function after we learned about compositions of functions, and we would decompose it. It was actually way back first semester, chapter 1, believe it or not. Decompositions of functions. And decompositions of functions, we would look on the innermost part of the function and try to figure out who is the most stuck, or who is the most within, or who is the innermost piece. And then we would think about who is outside that. What would be the next function? And then we would think, who is the outermost? And then we could do something like stating the innermost as h of x, g of x, careful, f of x, and then we could look at this whole big single function as the composition of one within the other. Ringing any bells? Making sense at all?
Yes.
Yes.
The innermost would be like the little baby Matryoshka doll. I guess you could have Matryoshka balls too, but anyway. Matryoshka doll, right? And then there's one that is within, and then there's another one that is within. Now, it doesn't necessarily mean that every single function has 3 pieces. Some can have 10, and some can have 2. Looking up here, do you guys see compositions of functions? Not here. What would be the within? X, whatever. F of x, we're done, right? What would be the within? X, the within, x, the within. X and x. But over here, what would be the within?
3x plus 2.
3x plus 2. Did you guys see this morning when I took that one and I was like, oh, you can't do this yet. Oh, you can, we have to FOIL. Would you want to raise this to the 5th power before you take a derivative?
No.
There's a better way. There must be a better way, and there is. It's called the chain rule. This one, do you see an innermost?
6x.
This one, do you see, well, there's not much going on, but one innermost, because the other one would just be x, right? One innermost. And this one, isn't his derivative easy? Forget him, plus, does he have an innermost? Yes. Chain rules, the chain rule, lets us deal with the innermost. And let me just give you a quick little peek at what's going to be going on. Let's get there tomorrow. I'm just going to go ahead and actually show you a few examples of me doing the chain rule. You've already seen it in your summer packet just a little bit with inner and outer. So let me just show you my doing a few. Then tomorrow we'll work through all the logistics of how it works and try to come back to it. But let's just do 2 different functions. Let's do one as y equals sine of 3x squared plus 1. And let's do another one of y equals square root of cosine of x. How would we normally take a derivative of, who do you see first when you look at nesting dolls all put together, Matryoshkas? The biggest one. So look at the biggest one first. Ignore the inner one. It's just chilling inside. How would we derive sine? Cosine. Have I peeled off anything yet? No, I'm just dealing with what I see. So what's still inside? But that poor little 3x squared has his own derivative. Chain rule says multiply. We peel off the sine, look within. The big one's gone now. Let's derive the inner. What's the derivative of 3x squared?
6x.
Guess what the final answer is? We write it differently just to make it look pretty, but we're done.
You would have to.
So how would we rewrite something with a square root? a 1/2 power. And how would we derive? Take down the 1/2, wait, make it a negative 1/2. Dealing with the outside, peel off the outside 1/2 power and say, oh hey, cosine, he has a derivative too. And his derivative is negative. We did 2 chain rules and barely talked about it. See you guys tomorrow. Finish 2-3 for tonight.
Did you eventually have to do the product rule?
Yeah.
If we did another derivative,
I was trying to get you lucky.
but in these ones there was no times yet.
Not burn. Never mind.
Bye guys, I'm just rewriting this to make it pretty. I'll see you tomorrow.
Wait, breakers. It's picking up. Oh, I heard grove. Yeah, I'm like, oh my god. This sucks. Yeah.
Yeah.